service. There's problems with this, and that's the plausible deniability. The idea is that if you brute force every key, you'll eventually have one that looks like all your base are belong to us, and the rest don't look like anything. So there's a lot of interesting ideas to fix that. Okay. And so then you type your message. I should probably do something readable like la yak or something. And then you go upload. And you put in a passphrase like test. And it saves it to the disk instead of uploading it to a server. But the idea is that you'd upload these to a server, and then someone would download them from the server. Or you could do instant messaging, groups. A lot of good ideas are out there. Hopefully, it has created a file called something or another. Yeah. Okay, so so the obvious, oh, great. Okay, I give up. So I can show you something even cooler, which is my TextSteg program that actually works. If we have Python, and it's tsteg a. Does that say what it's supposed to say? Okay, so you take a dictionary of words and you do some type of thing where you can transcode letter whatever to a large set of words. And for a test, I've decided to, good. Okay, so you get your secret, and then you type in your hex key, hopefully. And of course, it was written today, so that's, so 1, 2, 3, 4 is a good key. Uh-oh. Oh, yeah, because there can't be spaces. Okay. It's a very, very raw thing. Okay, so 1, 2, 3, 4 is a good key. Okay, and it comes out with something that looks like spam. Doesn't that look exactly like spam? What it is random words, right? Except that certain words are keyed to BL. And you can actually, the decode function comes out with BL, H, and then an extra N because I screwed up the code. And there you go. You can actually encrypt anything. And it looks exactly like spam, except that there's a problem in that if you brute force every key, you'll eventually find 1, 2, 3, 4 key that actually decodes to blah, and oh, we've answered it. And so that's a problem with steganography that has to be solved. Maybe massive, massive keys will solve the problem, or some exotic system. Questions? Ideas?
What's different about your tool?
Nothing at all. This TextSteg is as simple as you can get. It's simple steg. If someone were to create a TextSteg program, they'd probably write it in C, but it would do pretty much like this, maybe a bit better. Yep. I'm just implementing it. Implementing the good theories that are out there. Okay. If there's any, I'd like to plug a Neg9 group, which we meet in Seattle and Chico and everywhere. URL is neg9.org. Thanks.
Cool. I just love the fact that people are willing to come up here to share what they're working on, because that's what Toorcon's all about, is sharing your ideas and sharing your work. So it's nice to actually have a little bit of a venue for people to do that in here rather than the hallway where it normally happens. But we've got, you ready? We've got a few more people queued up. Again, if there's anything you want to talk about for 5 minutes, please go ahead and line up on the side of the stage and introduce yourself when you're up here, and you've got your 5 minutes of fame.
So I figured, 5 minutes, why not? I'm DJ, I'm over at UCSD, and so I briefly wanted to talk about hashing algorithms, because lately we've come to a realization that they all suck. MD5, of course, is increasingly broken in the last few years. SHA-1 looks like it's going, SHA-0 went a while back, and really it's going closer and closer, and Kaminsky, who's probably here somewhere and speaking at some point, has been taking Boeing web pages and Lockheed web pages and saying, look, they hash the same, and they're exactly the same thing, and we can totally exploit these minuscule vulnerabilities in hashing algorithms where as soon as you have one collision, you're screwed. The root of this problem really is in the Merkle-Damgard construction of hashing, and what that basically means is you take a stream and you break it down into blocks, and all of this attack is relying on one collision. You can take that block, you can determine that block as your condition code, and then output a completely different sequence that can hash the exact same thing. So really the problem here is not in either of these hashing algorithms, but in the construction blocks where we're taking stream algorithms in blocks. Now, if we do that differently, we can actually get a different approach. So, for example, if you take a standard algorithm that's badly broken, like MD5, and you break your data up into blocks, and that's how you get your hash eventually. Now, if you move everything over by a half a block and rehash it, and combine those hashes, you can get something completely different. You can also do some reordering. You can also do some masking. You XOR off based on the location of your block against the total block count, and then you mask that, and now not only do your collisions have to be special purpose for the data that you're actually using, but they don't have the same problem where Boeing's web page and Lockheed's web page encrypt to exactly the same thing anymore, because you actually have to hash, or you have to collide on two different data sets, and you have to collide on that boundary where you've moved and relocated elements. So really, I just wanted to come up here to say that anyone who does plan on making a hashing algorithm in the next few years, one of the things that you're probably going to see out of the new generation of algorithms is that they won't just be block-based, and they won't just split it up into simple blocks like you've been seeing for all of the hashing algorithms pretty much in existence so far, including, I believe, the newer Whirlpool and other types of things. Yeah. Yeah, two different hashes is also a solution that's been done, and it's a good solution, but there's some skepticism among cryptographers because they actually use the different hashing as vectors to attack the other one. It's tricky, and honestly, I don't know how they do it, but it can be done, and so two different hashing algorithms isn't honestly the best. It would be nice to actually have an algorithm that worked, and that as soon as you gained a collision, it wouldn't immediately deteriorate into something that's unusable. And really, the emphasis on that should be at the actual level where we split the data into blocks. There's a question back there. Right. Yeah, no, and part of you can go on Schneider's blog, and he has links to discussion notes, actually. And part of the discussion is that they're going to have to look at a different way of thinking about hashing algorithms. And, that is about the time to do it. And the block function is an important place to look at. Yeah. Right. But before I end, there's one place where I want to point out where this doesn't work. Excuse me, where Merkle-Damgard is why it was done and why we did it this way, and what the new generation of hashing algorithms are probably going to have problems with. And that is with streams that you don't have a bounded length for. If you don't have a bounded length, we have to use something like this. And we've always designed algorithms with the expectation that they're going to be used on streams, and we have to be able to use them on streams. If we throw that away, we can gain a lot of security simply by knowing the total block size. And then we can do some tricky things to actually put that data embedded in, mask it, and basically defeat those attacks, which is why I think hopefully we will be seeing something better soon.
Hi, my name is Ivan Krstic. How many of you guys have heard of the One Laptop Per Child project, also known as the $100 laptop? Excellent. So what you probably haven't heard is that we're actually putting an enormous amount of work into security engineering on these machines. And I'll tell you why I don't sleep at night. I don't sleep at night because we're building the largest monoculture in the history of the computing industry. So if we succeed, we'll have built 1 billion laptops that actually run largely identical software, largely identical OS images, and obviously this is scary. So it's also problematic because of the target users who, many of them have never seen computers before. Many of them are young kids who, you can't at all expect to have any idea of what constitutes reasonable behavior on the internet and, what computer security means. And we're actually doing a couple of radical things. So all of our machines will be running IPv6 by default. We're building up all the network infrastructure to use IPv6. Tons of security problems with IPv6. Really, the situation hasn't improved at all with IPv4. And there are a bunch of other things that are just sort of very scary when you start thinking about it. So one of the key goals that we have is to make these machines very hackable by the kids themselves. Hackable in the sense that we believe that there's actually a lot of value to being able to take your machine and rip it apart and see how it works and change it and put it back together. But when you're building machines that are explicitly designed to be very hackable, really this is in pretty stark contrast to having the machines be secure. And there are a couple of just things that I want to outline as brief ideas of what we have to deal with. One of the things that we're really insisting on is making collaboration more central to the user experience on these machines. So right now, if you're writing a text document and I tell you, well, grab one of your friends and collaborate with him on this text document, you really can't do this. The only way to do it is to specialize